Module 1, Enzyme Kinetics, Catalysis, and Regulation. Introduction. Welcome to Module 1 of the course titled Reservoir Engineering, based on the newly provided content outline. However, it is important to note that the topics listed, such as enzyme kinetics, enzyme catalysis, enzyme regulation, and molecular modeling of allosterism, are topics typically associated with biochemistry or enzymology, not petroleum reservoir engineering. Therefore, in this lecture series, we will interpret the outline accordingly and provide a comprehensive academic script covering enzyme function and regulation. This module will cover the foundational principles of enzyme kinetics, mechanisms of enzyme catalysis, and the regulation of enzyme activity. We will examine both steady-state and transient-state kinetic methods, explore the chemistry of catalysis, and introduce the concept of regulatory enzymes and multi-enzyme complexes. Section 1. Steady-state enzyme kinetics. Enzyme kinetics is the study of the rate at which enzymatic reactions proceed and the factors that influence these rates. One of the most widely studied models in enzymology is steady-state kinetics, which examines reaction rates once the enzyme-substrate complex concentration has stabilized. 1.1 Basic Principles. At the onset of an enzymatic reaction, substrate molecules bind to enzyme active sites to form an enzyme-substrate complex. This complex undergoes transformation, leading to the formation of a product and the regeneration of the free enzyme. In steady-state kinetics, the assumption is that the concentration of the enzyme-substrate complex remains constant over a significant period. This occurs because the rate of formation of the complex equals the rate of its breakdown, either into enzyme and product or back into enzyme and substrate. 1.2 Factors affecting enzyme kinetics. Key factors that influence enzymatic reaction rates include substrate concentration, enzyme concentration, pH of the reaction medium, temperature, presence of inhibitors or activators. The rate typically increases with substrate concentration until it reaches a maximum velocity, beyond which further increases in substrate do not enhance the reaction rate. This plateau reflects enzyme saturation. 1.3 Determining reaction velocity. To determine the rate of an enzymatic reaction, researchers measure the amount of product formed over time. By plotting reaction velocity against substrate concentration, one can derive parameters such as the maximum reaction rate and the substrate concentration at which the velocity is half maximal. These values help characterize enzyme efficiency and substrate affinity. Section 2. Transient kinetic methods. While steady-state kinetics provides a broader view of enzymatic activity, transient-state kinetics focuses on the early phase of the reaction, before the system reaches a steady state. This approach offers insights into the detailed mechanisms and intermediate steps of catalysis. 2.1 Importance of transient kinetics. Transient kinetics is essential when investigating fast reactions or when studying enzymes with complex catalytic cycles. It allows for the observation of short-lived intermediates and conformational changes that are otherwise undetectable under steady-state conditions. 2.2 Techniques used in transient kinetics. Common techniques include stop-flow spectrophotometry, enables observation of rapid reactions by mixing enzyme and substrate instantly and recording the absorbance changes in milliseconds. Rapid quench methods capture intermediate states by abruptly halting the reaction at specific time intervals. Flash photolysis, useful for initiating reactions with light and studying fast photochemical processes. These techniques provide time-resolved data, revealing how substrates bind, how intermediates form, and how products are released. 2.3 Applications. Transient kinetics is instrumental in drug development, mechanistic enzymology, and the design of enzyme mimetics. By dissecting each step of a reaction, researchers can identify rate-limiting steps, suggest modifications to improve activity, or inhibit unwanted pathways. Section 3. Chemistry of enzyme catalysis. Enzymes function as biological catalysts by lowering the activation energy required for chemical reactions. Their active sites provide a unique microenvironment that facilitates transformation of substrates into products. 3.1 Catalytic strategies. Enzymes employ several catalytic strategies, including acid-base catalysis. Enzymes donate or accept protons to stabilize intermediates. Covalent catalysis. A transient covalent bond is formed between enzyme and substrate. Metal-ion catalysis involves metal cofactors that participate in redox reactions or stabilize charges. Proximity and orientation effects. Enzymes bring substrates into close proximity and correct alignment to favor reaction. These mechanisms are not mutually exclusive and often occur in concert within the active site. 3.2 Transition state stabilization. A central concept in catalysis is transition state stabilization. Enzymes are believed to bind more tightly to the transition state of the substrate than to the substrate itself. This binding reduces the energy barrier and increases the rate of product formation. The design of transition state analogues, which mimic the structure of the transition state, is a key strategy in the development of potent enzyme inhibitors. 3.3 Role of amino acid residues. Critical amino acid residues in the active site mediate catalysis. These residues often include histidine, which participates in proton transfers, serine and cysteine, which act as nucleophiles, aspartate and glutamate, which serve as general acid or base catalysts. The positioning and chemical environment of these residues dictate the enzyme specificity and efficiency. Section 4. Regulatory enzymes and allosterism. Not all enzymes function at a constant rate. Regulatory enzymes can change their activity in response to internal or external signals, enabling fine control of metabolic pathways. 4.1 Characteristics of regulatory enzymes. Regulatory enzymes often catalyze the first committed step in a pathway and are subject to feedback control. Their activity can be modulated by allosteric effectors, covalent modifications, e.g., phosphorylation, changes in enzyme synthesis or degradation rates. These enzymes are crucial for maintaining homeostasis and responding to environmental stimuli. 4.2 Allosterism. Allosteric regulation occurs when a molecule binds to a site other than the enzyme's active site, causing a conformational change that alters its activity. This site is called the allosteric site. Allosteric enzymes display cooperative binding, where the binding of one substrate molecule influences the binding affinity of additional substrate molecules. This is often seen in enzymes with multiple subunits. 4.3 Molecular models for allosterism. Two primary models describe allosteric behavior. Concerted model, MWC model. All subunits of the enzyme switch between active and inactive states simultaneously. Substrate binding shifts the equilibrium toward the active form. Sequential model, KNF model. Substrate binding induces a conformational change in only the bound subunit, which then affects neighboring subunits sequentially. Both models explain sigmoid kinetics and are supported by different experimental data. Some enzymes may exhibit characteristics of both models. Conclusion of Module 1. In this module, we laid a solid foundation in enzymology by exploring the principles of enzyme kinetics, catalytic strategies, and regulatory mechanisms. We began with steady-state and transient kinetics, examined the chemical strategies employed by enzymes to facilitate reactions, and explored how enzymes are regulated through allosterism and feedback mechanisms. In Module 2, we will dive deeper into advanced topics including multi-enzyme complexes, enzyme assays, criteria for determining enzyme purity, enzyme reconstitution, and the regulation of both enzyme activity and synthesis.